I'm here to talk about human experience and artificial intelligence along the pathway to FWI for complex structure land seismic. I emphasize the word pathway because we're not there yet in having a complete FWI solution for complex structure land seismic data. FWI is a well-established technique that adds value in areas where you've got a high data density, high resolution, high bandwidth, and that's not the situation we're dealing with low signal density uh, and high geologic complexity. So I'll show you some of the problems we deal with and why we're encouraged that FWI is going to add value in complex structure land and what we're going to do to get there. So just a bit of context and how this work was as affected by Sam Gray's the honoree's work. Model building evolution started with was trying to solve these problems in complex structure land seismic data. The big limitations are data density because of surface access and other factors, which result in this low fold and low data density and some oftentimes low bandwidth because of the attenuating near surface. Speaking of the near surface, we've got a lot of complexity in the near surface. Erosional and depositional features result in velocity variation right along the surface due to weathering. We've got rough topography, and that in itself is a whole topic, and we'll address that a bit later. But when we look at, you've got, someone says there's 1,000 meters of elevation difference across a seismic data set. That's certainly a big number. But I tell you, it's a lot bigger looking bit of topography when you look at it on the human scale and you see this seismic crew from Colombia, this photo from Jaime Checa, and these guys are hard at work trying to get some decent resolution of the seismic data, dealing with surface conditions, and obviously there's going to be recording issues from the receivers and the sources along this rough topography. On top of all that, we've got subsurface complexity with folds and faults in our subsurface, velocity variation easily within a factor of 2, variation in velocity, and significant variation in seismic anisotropy. The velocity is higher in the direction parallel to bedding, and that direction of bedding varies significantly in the subsurface in these complex structure areas. So I mentioned our honoree Sam Gray and the manual tomography method developed in the late 90s that earned Best Paper in Geophysics in Volume 64 in 1999. And kudos to Sam for that paper, and also kudos to the Geophysics editorial board that decided that was the best paper in geophysics, because that technique is still adding value in exploration in mountainous areas today. Strategy here is interpretive model building based on the human experience, geologic constraints, that type of thing. And then what we thought a few years ago, Greg Cameron kind of spearheaded this initiative to say, okay, why can't we use AI to enhance this human experience method and use the convolutional neural networks to do model updates similar to the way the human does. So we want to give it geologic training data and see how the AI can do an update. Of course, once you see an update from AI, I want to make sure it makes geologic sense. So we loop back the humans into the process and see how we can refine that, and what have we learned from the data set, and what can we throw out from the AI method. And then the next step in this evolution is to go to full waveform inversion. And again, I've talked about all the limitations and bandwidth and all these things with these data sets. And yet after seeing the results of the CNN model updates, we're encouraged. And I'll show you an example of that where we are hoping that we can get increased model resolution from the wavelet characteristics, that manual or automatic reflection tomography will definitely not produce that information. So manual tomography, what's that all about? Well, I'm just going to show a quick example of a interpretive model building on the Benjamin Creek 2D data set. Those of a certain vintage will remember this line very well, from the Canadian foothills west of Calgary here. And it's got low data density. What the display shows, so it's a model building, a display. You've got the velocity models, velocity overlaid on the depth section. That's a pre-stack image gather, orthogonal to the line, and actually two of them. And if we zoom in on this, we can see that we've got fairly low data density in the near surface, which is the lens through which we image the subsurface. So further down, we can see we've got a fairly flat image gather, great. But I tell you that I wouldn't, there's not much to see in terms of the move out curvature in the shallow section to get the kind of detail we need. And that's the lens through which we image the subsurface. And that makes a big difference, as we'll show with this model scenario test. So let's imagine we've got the velocity model for the Bench Creek data set, and we've made this fault interpretation based on the footwall truncations, where the footwall reflectivity ends. Logical, that would be the fault plane. However, it does look like there's a reflector above that fault plane, and wow, that looks like it could be a fault plane reflector. And maybe we just haven't imaged the footwall very well. Maybe they haven't illuminated it with our seismic experiment. Okay, fine. So let's try these two hypotheses. And in the last 25 years, this has been a big difference in visualization and runtime, to be able to run migration in minutes instead of hours. And it's been great to be able to do a lot of different testing and to see how the imaging responds to an updated velocity. So let's take away the velocities now and look at this area of influence of that fault interpretation change. And you can see the reflectivity all the way down the section with this new migration is definitely showing favors the one fault interpretation over the other. And you can see how a small, reasonably subtle change in the velocity model in the near surface can propagate all the way down the section and affect the imaging right to the bottom. So this method works great, and we love it, and it's bringing a lot of success to exploration areas around the world. And we're hoping, like I said, Greg Cameron spearheaded this effort to use CNNs, convolutional neural networks, to update the velocity model. It's an iterative image domain velocity model building tool that leverages human experience and the predictive power of deep learning. So we've got the migrated gathers and a velocity model as input. We've got to train to CNN and predict any model changes that we need. So here's how the workflow goes. We call it CLIMB, computer leveraged interpretive model building. So we're still combining human experience with the artificial intelligence in an interpretive sense. So we have our representative synthetic training data. That's an important thing, right? We want to give a data to train on, and then we train the CNN. And we'll look at the training data in the very next slide. And then we've got a new data set in a new area, and we can build an initial velocity model and migrate that field data. And then we make a prediction using that trained CNN. And then we combine the interpretive and automated velocity models. We learn from it. We discuss the potential model changes with the interpretive team. We give a lot of credit to structural geologists in our work, not just to be nice, also mostly actually because it's true. Having a good geologic understanding that we get from the geologists adds a lot of value to the imaging in our projects. And so that's a human input to this whole process. Let's see who's doing what. The artificial brain is getting trained on the CNN. It makes a prediction on the model update. And then the wet brain, the human brain, has to find some creative and clever synthetic training data sets to train on. It also, the human also comes up with the initial velocity model. And when we have the updates from the CNN, the human judgment is important to decide what goes into that geological velocity model. So it's a real team effort between man and machine. And then onto this training data, it all should make geologic sense, and it does sort of. The geologically reasonable parameters to create representative models. So the kind of velocities we're dealing with, we've got this variable topography and these layers that have folds and faults. And of course, we want to make sure we've got this variable near surface velocities that we see on common in these types of data sets. And then we make thousands of them. Now, we say they're geologically representative. They don't necessarily make geologic sense, i.e. like they won't balance, but we're just trying to give it folds, we're trying to give it faults, we're trying to give it a variety of dips from flat to steep, and show the neural network what the relationship between the seismic data and the velocity model is. So we run the finite difference modeling, again, very representative finite difference modeling. So this is where the finite difference modeling development effort has been really important to us. And we do TTI acoustic forward modeling using DeVito. We add some wavelet distortions and noise, migrate the data using TTI Kirchhoff presec depth migration, and then we got our depth migrated gathers. And we say, hey, you know, this is what the model looks like, this is what the gathers look like. And then the hope is that when the CNN system sees an inaccurate velocity model, it's going to give us some guidance as to how to update it. So here's an interesting one. This is good old Benjamin Creek again. And the initial model was constant velocity. We thought, okay, let's see what the CNN can find. And it's actually a pretty good image, embarrassingly so, with this constant velocity. And then after the first iteration, you can see the CNN says, oh man, you gotta change the velocity in the shallow section. Things need to slow down. Again, the warmer colors are high velocities and the cooler colors are low velocities. And we go through these iterations. And by the time we get to like 6 or 7, you know, we're getting some pretty nice, clear, sharp boundaries where the stratigraphic changes happen. So that's very encouraging to have this kind of geological look to the section. I was really displeased by this strange artifact in the model building, and for some reason, as the iterations went by, the CNN really doubled down on that and said, "Yeah, no, this is really a thing, guys." So we had to look at this, and we thought, well, you know, that's about the size of a seismic wavelength. So for surface seismic, so it's not something you'd see on move out on gathers for manual tomography or even automated tomography or anything. It's going to be a wavelet characteristic thing that the CNN sees in this case, if it actually exists. So I gave Greg the benefit of the doubt, and I called Andy Newson and said, hey bud, can you send me like the sonic log for this and let's look at this. And Andy gave us the data, which was great. Also gave us a bit of an interpretation of this. So here's the velocity model in that the CNN found in orange, and here's the sonic log. So a pretty good match generally. This is the big surprise though. At the top of the carbonate platform, there's a coal-rich shale layer sitting right on top of the carbonate platform that creates this big velocity inversion. And yeah, lo and behold, there it is on the sonic, and there it is on the seismic data. So the CNN found that. And I thought, wow, that's fascinating that it's finding this information. So this is just basically, statistical weights with convolutional neural network. Perhaps the FWI can do a good job on using that. So that's part of the motivation for it. Another motivation is we've got we see the potential of getting more information from our seismic data. And we have preliminary early arrival FWI results on Sam Gray's Model 94 synthetic foothills data set. So we'll look at that in more detail when we talk about RTM, which is also on our pathway. So here's our input model for this, and here's the diving wave FWI. So it's basically just the early arrivals from used in the FWI inversion. And yeah, sure enough, we're getting these little synclines down near the surface are showing up. This funky business down here with this big S-turn in the velocity model, and that's there. We'll look at that later. And sharpening up this, little cardium, I guess, sandstone in here. And it's really getting the detail that we're hoping to see. There's also some artifacts and some other things. So we definitely want to use prudently, but it looks like a high potential. So just a few words on RTM, and then I'll wrap up. So RTM versus Kirchhoff. Kirchhoff is the workhorse, continues to be the workhorse in exploration in these types of areas. It's a great seismic imaging method. It uses a high frequency approximation. It's a wave field represented by rays, basically. And the RTM, we're propagating waves into the subsurface, and it shows improved imaging where the ray tracing breaks down. So extreme velocity contrast and strong velocity inversions. And we'll look at that here on some synthetic data, and actually we'll loop back around and look at that on good old Benjamin Creek. So we needed an RTM that was specific to our geologic setting, and this is a great place to test our finite difference modeling system, and a lot of refinements happened as we looked at how what's wrong with our RTM and how to get it nice and optimized. So the majority of RTM algorithms are built for marine imaging and don't account for varying topography. And we've developed an RTM to specifically handle the complications of complex structured areas. Our input data contains a depth weathering solution, or DWS, and it uses the near surface model from the first arrivals or early arrivals and model move out reflection statics, which are coupled to the velocity model. So we can throw out the complete time, the complete weathering solution from the time processing, no statics, none of that goes into this. We've got a complete depth solution. And then, and like I mentioned earlier with this, with the interpretive model building method, the velocity model is constrained by geologic understanding, seismic diagnostics. So let's look at this problem of wave field interactions at surface. So this is where we really dug deep into this whole situation with the surface and the near surface. Their irregular topography does not fit within the orthogonal grid. Topography values get truncated to the grid, and it creates this numerical noise, not a geological noise, but a numerical noise, stair-step surfaces and scattering noise. So we've implemented these two different surface boundaries, the free surface, obviously the sky and the ground, and the attenuating near surface. And in order to use these surface boundaries, we use a technique called immersed boundaries. Tim did a lot of effort on this, the research in it, and how to apply it, and it's worked really well. And immersed boundaries are developed to simulate cardiac dynamics, so you're some sort of finite difference modeling of heart characteristics, and you definitely want a nice curved surface. And so then with these immersed boundaries, instead of changing the computational grid, we change the equations interacting with the boundary, and then we use the grid point distance from the topographic surface to update the computational stencils. And let's, in a functional way, let's see how that works on this awesome synthetic data set that, anyway, huge contribution to seismic imaging research from Sam Gray. That's, again, still 30 years later, is still adding value to our community. The old Model 94 velocity synthetic seismic data set. And that's not a great name. Sorry, Sam, but that's, you could have been a little more creative with this whole thing, and maybe you didn't think that 30 years later it would still be such an important part of imaging research. But it's got all kinds of great features in it. Again, this was this weird S-turn that we looked at in the FWI model earlier. And we've got this overturned limbs, we've got folds, we've got faults, you've got 1,000 meters of elevation. This is the real thing, right? And it's super valuable. I remember in the 90s, Sam explained to me that some of these curvatures of the synclines are basically designed to make a Kirchhoff migration blow up if the amplitudes aren't properly managed. So that's a really great QC tool, certainly for development, and it's been very valuable. And here's the benchmark Kirchhoff from the original paper, 1995, migration from rough topography, I mean. And yeah, great looking, lots of detail, right? The Kirchhoff is really doing a great job finding all the major features, leading edges of structures, not so much, and the overturned limbs, not imaging. And we're losing some detail in the shell section, but it definitely has a lot of 90-some% of the features are imaged really quite well. And then 20 years later, we've got the kind of a benchmark Schrag publication in geophysics, RTM from topography. And this uses this curved grid strategy. And if we compare this back to the Kirchhoff, you can see the incredible amounts of detail we're getting, particularly in the near surface. It's really showing impressive improvements over the Kirchhoff. And we're getting these overturned limbs and some other features. And so now we're in kind of a 99% kind of solution, or 95, as opposed to 90. But the thing with this curved grid, this is actually from the Schrag paper, and just overlaid it on here. You've got this curved grid that they use to make sure that the surface is honored. But you've got some variability in density in the wave propagation in the subsurface. It's also labor intensive. Like the grid has to be redefined for every data set, because every data set has a unique elevation representation. And so let's look at the implications of this curved grid, this mountain to the left here that I've indicated. Here's the curved grid RTM, and then here's with the immersed boundary RTM. And you can see, I'll just get zoomed in here. You can see the detail we're getting in the very deep section over the anticlines, like top to bottom. We can see imaging differences with the immersed boundary versus the curved grids. And this was the big surprise to me. I didn't anticipate this level of detail that was in the original Sam's original model is showing up so clearly. I was stunned. I knew that was there in the model, did not know that it was actually recorded in the synthetic data set. So it's impressive that that was recorded and it was imaged. So that's great. Okay, but that's synthetic data. Let's go back to reality and look at the good old Benjamin Creek data sets. Here's the Kirchhoff versus the RTM. And yeah, very comparable. That's good news that the RTM is working really nicely. Kirchhoff is the workhorse for depth imaging and continues to add value in exploration today. And but it's the 95% solution, and the other 5% we get from the RTM can be quite significant. So let's look at this in area 1 here on the left. The blue is the Kirchhoff, and the green box shows the RTM. And yeah, we wouldn't be doing a lot of scenario testing with that fault plane with the RTM because we know where that fault plane is now. It's clearly imaged, and that's great. Rays have a hard time with synclines. Box number 2 shows the improvement in imaging, the coherency throughout, and the seismic character throughout the syncline. And more importantly, the targets below the syncline are imaged much better with the RTM. And in the top right, box number 3, again, these steep dips give us an opportunity to correlate surface geology to the seismic reflectors and help us understand the structural shapes much better. So just to summarize our pathway to FWI, these are the ingredients as we see them for FWI and complex structure land seismic data. Finite difference modeling that handles rough topography and TTI anisotropy, and that was really borne out by the testing and development of the RTM. We have a development path with industry partner DeVito Codes with a proof of concept that have the finite difference modeling engine, which drives CLIMB and RTM, both in production and with a lot of different case examples. So that's really working, and we have this joint FWI development in progress. It's in progress so much that I got that image of the early arrivals from Tim on Friday. And a key ingredient for FWI, which is perhaps overlooked, is an input model that's accurate. We want an accurate input model to the FWI, and currently in these geologic settings, the most accurate PSD and velocity models come from geologic constraints and human experience. The human experience models with AI refinements will be a strong foundation for the FWI workflow. Thank you for your attention.